parts. Today, we're going to crank through two sections. We're going to talk about integration by parts and another type of differential equation. My being upfront with you guys, both of these topics are BC topics, would not appear on your AP calculus exam that you will take, but are standard like Calc 2 skills that in your second year calculus class you will see. So they're on the syllabus. We do them because they fit pretty nicely into what we've been doing. Yeah, Emma.
Have you graded the test yet?
Mostly.
How do you feel about that?
There's a big difference between second and third period for some reason, which I thought was kind of odd, but...
As in we did better or worse?
Well, the class that took it later seemed like they kind of knew what to expect a little bit more.
Oh, that's interesting.
Yeah, I thought so too.
Oh, what the heck? I get it now. No.
Anyway, we'll probably have those back and ready for you guys here another day or so after I figure out what we're doing curve-wise or whatever. Anyway, let's get to this and we'll talk some more at the end. Is that okay? Emma, are you happy with that much? All right. So we're going to talk first about integration by parts and then talk about linear differential equations, which is another class of differential equations. So with integration, we have like U substitution that can kind of run the chain rule backwards. We don't have another integration technique to take care of quotients aside from like, oh, well, depending if it's like, maybe I can make it work as a tan inverse, or maybe I can do a partial fraction decomposition, or I can do like a polynomial division thing to make it like into a form I can do something with. But in general, we don't have like a one-shot formula for that. Now, when we take the other one to consider, the other special derivative rule we have is the product rule, right? When we do the product rule, we get the sum of two things, right? Everybody's okay with that?
Yeah.
So if I want to run the product rule in reverse, an integration rule to undo the product rule, that doesn't quite work because the odds of having something times something plus something times something, you just don't run into that a lot. What we'd rather have is a integration technique that can deal with the product of two functions that are not U-subbable. That's what we're going to be looking at today in this integration by parts. And the basis for that still is going to be the product rule. So if you guys remember, with the product rule, if we take the derivative of two functions, f of x times g of x, the result is f of x times the derivative of g of x plus g of x times the derivative of f of x. If we then like integrate both sides, that's going to cancel, and that integral will distribute through, right? So that's kind of what we have here. I've just flipped it around. So this is my product rule with the derivative canceled, right? And now what we'll do is we'll just subtract or distribute our integral through. And if we subtract this over, we have a integration rule that we can use when we have the product of two functions. This is what we call integration by parts. So the classical way that we write integration by parts is with like u's and v's. So we say the integral of u dv is equal to uv minus the integral of v du.
May I just put in?
Yeah, go ahead.
Thank you.
It's all right. So that's a formula. Now, the catch here is that we're going to have to pick the stuff we want to be our u and the stuff we want to be our dv. So in general, we want to pick our u so that the derivative becomes simpler and our dv so that it's easy to integrate. Everybody's okay with that? All right. So we'll do some examples of this, and then we're going to move on to the next thing now. But it's basically just using this formula. Okay? All right, so let's take a look at our first example. Here is the integral of x times sine x dx. So the first thing we want to do is decide what stuff is our u and what stuff is our dv. So we know the dv is going to obviously get the dx part, right? And we have two things left. We have x and sine x. Which one of those gets simpler when we take the derivative of it? X, right? So let's make that our u, and let's make sine x our part of our dv. Everybody feel okay there? Okay. So now du dx is going to be, no, du dx 1, or du is going to equal dx. Everybody's okay there? And the integral of dv is going to be the integral of sine x dx, right? What's the integral of dv equal? You mean v. And the integral of sine x dx is negative cosine, right? Because the derivative of cosine is negative sine. Is everybody okay? All right. So that's, I need these two additional pieces. Let's just, for our formula. So if I go back to my formula now, so I have this integral is u times v minus the integral of v du. Is everybody okay with the setup so far? I'll pull that negative sign through. What's the integral of cosine x dx?
Sine x.
Yep. And then plus c.
Why did it turn to a plus? Like, where did that one negative go?
There's two negatives, minus a negative cosine.
Yeah, but the negative cosine turns into a positive sign, so wouldn't it still be negative?
The antiderivative of cosine is positive sine.
Okay.
Because the derivative of sine is positive cosine.
Okay.
So I just grouped those two guys together to make the plus.
Okay.
Is that okay?
Yeah, the integration.
What's up?
So I get how you identify u, but how do you identify dv in the equation?
I picked the thing that got simpler when we take its derivative. I want that to be my u. And the other stuff then that should be easy to integrate should be my dv.
Okay.
That's our choice, though. Mm-hmm. All right. Let's look at the next one. So here we have the integral of the natural log of x dx. It is worth pointing out, I guess we should have done this before we started here, that you could not have u subbed the integral of x times sine x, right? If you picked u to be x, then you just have u sine u, same thing that you had before. If you pick sine u to be x, or sine x to be u, well, when you do the derivative, you got cosine u, and there's none of those floating around anyway. It's like intractable to try to u sub it. Yes, Pete?
So would they ask, like, do this by integration by parts? Or do you just have to know?
On your AP exam, this will not be covered.
Yeah, but like in general.
In general, no.
Okay.
They would expect you to recognize that, like, this is not u subbable. I should try something else.
Okay.
Usually when you see the product of functions and there's no u substitution obvious, integration by parts is probably the way you go. All right. Here we have the integral of the natural log of x dx. Do we have a antiderivative formula for the natural log? We know that the antiderivative 1 over x is the natural log, but we don't have a formula for the integral of the natural log. Right? So there's no way to do this as it's currently constituted. This needs to be done by integration by parts. All right. So dv needs to be something that's integrable, right? Or easily integrable. Is the natural log of x going to be easily integrable? Clearly not, or we would just do it from the start, right? So my dv must just be dx, which means my u has to be ln x. Everybody's okay with that? The derivative of u is 1 over x, so du is 1 over x dx. And v is going to be the integral of dx, which is just x. Everybody okay? So this is going to be u times v minus the integral of v du. So again, uv minus integral v du. Is everybody okay?
So is the du 1 over x dx?
The du is 1 over x dx. So 1 over x times x is just 1, right? What's the integral of dx? Just x. And we tack our plus c on and we're done. Is that okay with that? Okay. All right, let's look at our next one. what do you guys want to pick for u here? Yeah, that makes the most sense to me. And that means dv then should be e to the t dt. So can we do du without writing down all the notation? Okay, what's it going to be? 2t dt, right?
Oh, yeah.
Because our variable's a t this time instead of an x. I heard a lot of 2x dx, which is the right idea. Everybody's okay there? Can we do v without having to write out the integral? It's just e to the t. Everybody okay? Again, like, if you can't, write it out. Do the rearrangements, it's fine. I'm just trying to, like, streamline the process here a little bit for us as we've done it. This is our third example now. Yes, sir.
So you take the derivative for u, but you take the integral for dv.
Yeah.
Okay. I just want to make sure I got the word down.
Mm-hmm. Okay. So now we have u times v minus the integral of v du.
Oh.
Yeah. Uh-oh, right?
Oh, no, I was saying like, oh, it looks simple, but I guess not.
What are we going to do with this?
Do it again. Do it again.
You want to do it again? Yeah, I think that's right. So what should our u be this time? 2t. And our dv? Okay. So our du then is just 2 dt. And our v is still e to the t. So we still have this t squared e to the t. We have minus. Now we're going to have u times v minus the integral of v du Is everybody okay? Does it help me color coding things? Now the integral of e to the t times 2 dt, can we do that?
Yeah.
You better believe it, right? We just pull the 2 out front and just the integral of e to the t, no problemo. So we have t squared e to the t minus 2t e to the t minus 2 e to the t plus c. Lucia. Oops. That should be plus. I'm sorry, go ahead.
Did you get 4 tissues?
I didn't. Yes, of course. Adrian.
I'm just confused, like, wouldn't you get the same thing if you just did a product rule? Like,
So product rules for derivatives. We're doing an integral. So if I differentiated the thing in red that I've circled here, it should simplify back down to give me this. But running that in reverse is basically what we've tried to do here. Where were you thinking you're going to do a product rule at?
like after you got it, did the formula the first time, and then it's the integral of e to the t.
So the product rules for derivatives, right? The product rule isn't going to help me integrate this.
Like, wouldn't it just be 2t times e to the t, and then e to the t times 2?
So that would be if I asked you to, if you wanted ddt of e to the t times 2t, that would be, yes, like 2t e to the t plus 2 e to the t. But we're not differentiating, we're integrating.
But it's like the same answer. So I guess what's the difference? Is it the plus c?
So what is the difference? The difference here is that the derivative of e to the t and the integral of e to the t are the same thing. That's why it looks like it's the same. But it's not the same process. It only worked out this way because the derivative of e to the t and the integral of e to the t are both e to the t. If it was any function other than e to the t, this wouldn't have worked this way. Does that?
Yeah.
Okay. Okay. Yeah. Took me a minute to why is that doing that? What is the coincidence here? Oh, I see. All right. One more example here. Okay. Yeah, so this one, it's not obvious what to do, right? Because neither one are going to get simpler when you differentiate, and both are probably equally easy to integrate, right? So to me, this is a guess. I'm just going to try one way and see if it works out, and if it doesn't, okay, let's try the other one. Because I don't know that there's an obvious, there's nothing to me looking at this says I should do one thing versus the other. Does that feel okay? All right. So David, you said you wanted to do sine x for u and e to the x for dv.
Yeah.
Okay. So then obviously v is still e to the x, and du is going to be cosine x dx then, right? Okay. So e to the x sine x dx is going to equal u times v minus the integral of v du. This looks like I'm going to end up in a loop here, right? Because if I do this again, I'll end up back with the thing that I started, and I don't like the way this is heading, right? So I think this is, we made a bad choice. That happens. Sometimes it's, you just don't pick the right u and v. Let's try it again. So this time we'll pick u to be the e to the x and the dv to be the sine x. Bless you. So du is going to be e to the x dx, and v will be negative cosine x. Everybody feel okay? Okay. So we have u times v minus the integral of v du and that looks basically the same thing, right? Okay. make an obvious mistake, or is this one where we just kind of take a look and see what we're doing wrong here? You absolutely could. That's not wrong to do, although I don't think it's going to be helpful in this situation. Methinks that there is one other option to try. Uh-huh. Oh. Okay, I see it. Okay. So, let's stick with that first one. And while we haven't it doesn't appear like we've accomplished much, the loop is actually what we're looking for. The loop is what we want. Yeah. So let's see let's just demonstrate like how that loop is going to pay off for us. Almost.
Series.
Okay. All right, I'm going to distribute this negative sign through. And that's basically going to do going to nix that guy. So this is what we have, right? Take a look at this. And take a look at what we started with. You can go somewhere else. Live somewhere else. Did you guys notice?
Yeah, cancel out the integral.
Well, it's not canceling it out, but we can add them to the same side and get 2 e to the sine x dx equals sine x e to the x minus cosine x e to the x. And then we just divide both sides by 2 and slap a plus c on the end. And we got it. That's the answer. So we're right on when we're like, oh, there's going to be a loop. We don't want that. And it's like, actually, if we're back to where we started, we can just like combine those 2 integrals and then divide the coefficient back over and we're done. Yeah, you like that? No, you probably don't. No. But the takeaway here is the perseverance piece, right? That like sometimes if it doesn't look like something good is happening, maybe give it a little bit more and see if something good ends up shaking out, which is kind of what happened here.
Will there be questions in the AP where like you can't use substitution? Because I know you said that this wouldn't be in the AP, but would there ever be a scenario where we like wouldn't be able to use substitution? Or what?
Yeah, if it's on the calculator section where they expect you to do it on your calculator. So yes, they could easily give you an integration by parts, but it would have to be on the calculator section where you can just type in your calculator to get the numeric answer out of it. That would be reasonable for them to do. All right. One more example, doing by parts, this time with the definite integral, and then we're going to move on to the next stuff. Do you guys feel okay?
Yeah, that was good.
Okay. Again, the hardest part is usually choosing your u and dv. And after that is just kind of following the formula. All right. What are we going to choose here? I mean, there's really only one option here on this, right?
Yeah, go back. You're right.
I mean, it's just kind of unfortunate, right?
Yeah.
But the du only comes in one place, so it's not the end of the world. All right, so we have then... Oops. Okay, so we have u times v minus the integral of v times du and that's all, and this is still from 0 to 1. I guess that guy should have the evaluate from 0 to 1 on it. Everybody's okay? All right. So how are we going to do this integral over here? So u sub so we're going to have then, let's plug this stuff in, might as well, right?
How's the test for
The test forecast? What, the test for this chapter?
Is it not skies for the whole week or not really?
I don't know, like we're still kind of getting there. So again, just grind that out then.
Yeah, you'll bet.
And you got your values, you know. So there we had to do a u sub after we had done our integration by parts, and that's not uncommon when doing an integration by parts problem, is you get it simplified down into a u sub problem, and then you have another layer inside of it. Again, will this be on the AP exam?
No.
No. Okay, so take a deep breath. Would it be a main point of emphasis on the test I'm going to give you?
Yes.
No, no. I'm going to emphasize the AP pieces. It'll be on there, but would not be like if you screw up your integration by parts stuff, like I'm lost. Be like one question out of the test where you would need to do parts on, kind of thing. You know what I'm saying?
Yeah, that makes sense.
Okay. Again, it would be there, but would not be the primary focus. Okay. All right. I'm going to call this good for this section. What we're going to talk about next is another type of differential equations. So last time in 9.3 we talked about separable differential equations, right? Where it was easy to get all the x's and y's on one side. Here we're going to talk about a type of unseparable differential equations called a linear differential equation and how to deal with that. Okay? Now, will this topic appear on the AP exam?
Oh, no.
No, this is BC only. Will it appear on the test I give you? Yes, but like one question.
Yeah.
Not the main point of emphasis, but one. Okay? So we say that a first order linear differential equation can be put into the form dy dx plus p of x times y equals q of x. Okay? What does first order mean when we say first order differential equation? Has only first derivatives in it. Doesn't have any second or third or fourth, like just first order is first derivative is your biggest derivative in there. Okay? So, for example, if I have this differential equation, and we try to do this by separation, there's going to be no way to get y times dy on one side here, right? You should probably be able to see that fairly cleanly. So what do we do? It's not going to be separable. Well, here's the idea. So if I think about x times y, and I think about its derivative, that would include doing a product rule, right? We'd have x times the derivative of y plus y times the derivative of x, which would just be 1, since it's a derivative with respect to x, right? That's why y is y prime and not, it's like 1 times dy dx. It's like an implicit differentiation kind of thing going on. Okay. Well, that's exactly what we have here, right? So if I take this, I can rewrite it there, and then I can just integrate both sides with a little bit of sloppy notation because I don't have dx's where they're supposed to be, but it's fine because the dy dx isn't really a fraction. We just kind of treat it that way when we do differential equations. And we'd be done, right? Because the integral cancels the derivative, and then this is an easy integral to do. And we can rearrange some stuff if we want to, but that's the idea of what we want to have happen. Possibly, but not always. There's a reason why I did the integration by parts before I did this, because the integral can run into an integration by parts situation, but doesn't have to. Brooks?
Is every single question going to be set up with x prime y plus y is going to be like in that format, so then we're able to...
No.
Ooh.
So what if it isn't an obvious, like, oh, I can just pull this together as a product rule? Well, what I want to do then, if I have just some linear differential equation, what I want to do is I want to multiply both sides of this by some function. We're going to call that function I of x. we're going to refer to I of x as something called an integrating factor. And we're going to pick that I of x so that when I multiply it by the left-hand side, that left-hand side then will just be the derivative of I of x times y. Now, I haven't told you how we're going to choose that I of x, but it's possible to do that every single time when we're in this form to choose a function I of x so that when I multiply it by both sides, the left-hand side collapses down into a product rule derivative, and then I can cleanly integrate both sides and be along my merry way. So let's just kind of show you what's happening. So we start with our linear differential equation. And then I multiply both sides by this integrating factor. Now, by construction, I know this collapses into just the derivative of I of x times y. I've chosen I of x in such a way that that has to happen. Just like when we do the completing the square, whatever we add forces a perfect square to factor out, right? It's kind of the same idea. So now notice that everything on the right-hand side is in terms of x. So we can cleanly integrate both sides. On the left-hand side, the integral cancels the derivative. The right-hand side, though, may involve an integration by parts, because you see we have the product of two functions. So mark that's where the integration by parts may come in, is because I have the product of two functions there. But it doesn't have to, right? We saw if we had like x times 1 over x, or 1 over 1 plus x squared, we could just do that with a u sub. So it depends a little bit. So then I can just divide both sides by I of x, and this will be the form of my final answer. So here's the hard part. How do I find this I of x, right? Up to this point, we just assumed we could find it. Here we need to talk about how we get it. Everybody ready? Do you want to just see the answer of how to choose it, or do you want to see where the answer comes from? Okay. All right. So we know that when we multiply both sides by I of x, we know that the left-hand side has to collapse down into that derivative, right? Okay. So I'll distribute the I of x through, and then I'll expand this into its product rule derivative. Okay with that? So if I look at what I have, these guys I can subtract from both sides and cancel out. So that gives me this stuff. And I can divide both sides by y. That's going to give me this. And notice that this is now a separable differential equation, right? So I can divide both sides by I of x to get the I of x and derivative of I of x alone on one side. And if I integrate both sides, I'm going to get the integral of p of x dx plus c equals the natural log of I. I can then do like exponent base e to both sides and get that I is equal to a times, because that's the plus c coming out to the coefficient, right? This is like my e to the c, times e to the integral of p of x dx. But this is how we choose our I, is this formula. A is just e to the c, yes. Yes. All right, you ready to do an example where we actually do this now? Yes. I think that's probably for the best, right? So again, here is the formal. This is the piece that you really need. All right, so the first thing I want to do is I want to make sure that my starting equation is in the linear form. So that's y prime, right? My p of x is that 3x squared. And then my y. And then I have my, oops, I thought I picked a color there. And then I have my q of x, which would be 6x squared. Does everybody feel okay? So I am in that proper form. If I wasn't, I might have to do some rearranging so I can identify like what, p of x and q of x are. I think that happens in the next example. So the first thing I'm going to do is compute my I of x. Is everybody okay with that? What is the integral of 3x squared?
6, 3 times x, 3 over 3, 2x.
Right, just that.
Yeah.
Okay. So far, so good. So I'm going to multiply that to both sides of my equation then. So far, so good. Now, here's the beautiful part. This collapses down to just the derivative of I of x times y. Don't look at it like you're supposed to see it, because I can't see it, right? I just know that we've constructed our I of x so that this has to happen. Okay? It's not obvious to look at it that like, oh yeah, of course, that's that product. No. Most of us won't see it. Just know that that has to happen because of the way we've constructed our I of x. I know. Brooks.
Where did 6x squared come from out of that equation?
It's the original equation. Just it's okay. So far, so good. Everybody's okay? So that stuff just cancels out. And then how am I going to do the integral of e to the x cubed times 6x squared? It is a u sub. What will my u be?
6x squared?
Nope.
X cubed.
X cubed, good. So du is going to be 3x squared dx. So when I do that, I'm going to have the integral of e to the u 2 times du.
Oh, I get it.
So that this is just e to the, or 2e to the x cubed. And we should say plus c. Everybody okay? David?
For the first part of it, integral dx times y, how do you get that just cancel out?
Because it's the derivative of e to the x cubed times y. So the integral just cancels the derivative,
Gotcha.
which is the, yeah,
I thought that.
good. And then to get the y by itself, and we're done, right? You can do some rearrangement here, but like, for all intents and purposes, that's fine. Let's do another, right? Because this is what we're doing, not easy. Okay? It's not easy. It should feel like you're really stretching. This is like one of the, this is a difficult BC topic. Once you got the hang of it, it's like, oh, they're kind of all the same. But like the notation's a little hard. Like, okay, I just have to accept that this works is a little hard. Even though we went through like why constructing it this way is guaranteed that it works, but like it's not easy. All right, so the first thing I look at is this guy here. And I notice that, hey, this is not in the linear form, and I can tell right away it's not because the dy dx isn't by itself. But it sure as heck doesn't look separable to me, right? If I try to multiply through by dx, I'm going to have no hope of getting the x's times dx, right? So it must be able to be put into the linear form. So what I'm going to do is I'm going to divide everything by x squared so that I can get this into the linear form. Everybody's okay there? So this is like y prime plus p of x, y equals q of x. Everybody feel good about this now is in the linear form?
Because y prime needs to be by itself.
So p of x is 1 over x, q of x is 1 over x squared. All right. Next up, we're going to construct our I of x, which is e to the integral of p of x. What's the integral of 1 over x? Great. And what does e to the ln do? Just left with x, right? We can drop the absolute value. Yeah. You know why we can drop the absolute value? Because we're given that x is greater than 1, or greater than 0, so no harm in dropping it. Okay. You guys ready then? So multiply both sides of our equation now by x. Oops, guess we did green for the brackets this time. You guys have left me. I didn't leave myself enough space here. Go down. All right. This, we know, collapses down into I of x times y prime. And the left hand or right hand side just simplifies down to 1 over x. We do the integral both sides. Integral cancels with derivative. The integral of 1 over x is just the natural log of x. Notice I didn't use absolute values again because I know x is greater than 0. I don't have to have it. Plus c. And then we have y is equal to natural log of x plus c over x. And I think it asks us to solve for c in this problem because they give us a boundary condition. So I plug 2 in for y and 1 in for x and solve for c and then rewrite, but I'm not going to bother with that right now. Is that okay with you guys? I trust at this point that's fairly easy for us. Okay. I'm going to focus on the stuff that's I know is going to be hard, right? All right, you want to do one more? Or we feel okay?
I feel good.
Anyone else want to venture an opinion? Happy to do more.
I just had a question about the last one.
Okay.
So why, can you explain what parts turn into which parts when like x times dy over dx, like it turns into x times y, and that's all primed?
I mean, I can, but it doesn't matter.
Okay.
It has to work that way as long as you construct your I of x using the formula we've described.
Okay.
It guaranteed to work that way.
Okay, so then is the x like that's on the leftmost side, is that the same as the x inside of the parentheses right there?
So this guy out here is like my I of x.
Okay.
So this is always I of x times y.
Okay, I get it now. Yeah, thank you.
Mm-hmm.
I'm all good.
Okay. All right. Well, if you guys are all good, we'll tack on the 7-1 and 9-5 into the next problem set. So I'll update that on my Notre Dame here. And we are quickly closing in on final test. But we'll talk about what we want to do format-wise on that. So for for the integration by parts, 3 through 17 odd. And then for 9.5, that was 1 through 19 odd. Easter Sunday. Okay, got that all in there. And then what did I have on the agenda for tomorrow? 7-8. Oh, perfect. So on 7-8, we're going to talk about improper integrals. Or on Wednesday, we'll talk about improper integrals. And then when we get back, we'll talk about using differential equations to model and trigonometric substitution. And those will be the last 2 topics for the final test. So this will try to condense and not make this too expansive. So the topics we'd be looking at are, like slope fields, like solving separable and linear differential equations. There'd be like a modeling with differential equations component that's a little light, and then integration by parts and improper integrals. That's it. That'd be like the set of topics for the final test. We'll talk about the final test format when it gets a little closer, after you guys get back from spring break and I have a chance to really think about what's going to be the most beneficial for all of us. Probably not taking it. Thanks for that feedback there.
So on our plate right now, is it 4 problem sets? 9, 2, 9, 3, 9, 5, and then 7, 8.
It was 9, 2, 9, 3, 7, 1, 7, 5, or 9, 5.
Okay, so
Yeah. So again, it's like the first. I have the sections in order of what we've done under
those are all good.
Easter Sunday is the due date that's set for those.
Back to school like today.
No, you have another week off.
Yeah.
Oh, so that's this Sunday?
Yeah.
Yeah.
Okay, sorry.
That's okay.
I'm just thinking a lot.
But the following week is like your week of grace anyway. Like I don't really assume many people are going to have, if they don't do it by Wednesday, they probably aren't going to do it for Sunday. And they'll just catch up with it, the following Sunday sometime.
Are you gonna be checking papers on Easter Day?
No, but I never check papers on Sunday anyway. I do it on Monday.
Oh yeah, that's a good point.
So I conceivably would check things on Monday. But realistically, like, as long as it's in by the following Sunday at midnight, you still have your week of grace or whatever. You know what I mean?
Yeah.
Yeah.
Try not to make this harder than it needs to be or more painful than it needs to be. So yeah, that's the story. So you have what is it? We're doing improper integrals next time, and then so 3 more sections, and then that's all she wrote. So that should be plenty of time to do last assessment, and then have some review and get you guys as tuned up as we can before you guys hit the road and have to do it on your own. But
How many days, like school days, is there after Easter break? Is there
no clue, man.
Like 15.
Yeah, there's only 5 classes for each.
Oh my God, it's like 10 days.
you gotta start studying?
So,
I'm
what
really
you're saying
surprised.
is, we just.
Including everything.
I feel like we're like halfway done the semester. Like we're gonna be wrapping up. I don't even feel like we're